Okay, so we're now going to move on to the second component of the internal energy equation, which is heat. And we're going to try to think about how we can calculate heat that is transferred in a chemical reaction. The term heat transfer or heat flow is not quite correct because heat itself is the method of energy transfer or energy flow. So there's two ways you can transfer energy: through work, which we talked about before, and now the second method is through heat. The way you transfer energy through heat is by having two systems or a system and a surrounding where the temperature is unequal to each other. And so the higher temperature system or surrounding, either way, will then transfer its energy through heat to the lower temperature system. And the transfer occurs through collisions because the higher temperature system has higher kinetic energy, as we discussed in chapter 5, and lower temperature system has lower kinetic energy. So when that interface between the two systems or the system and surrounding happens, the higher kinetic energy molecules will then hit the lower kinetic energy molecules, and then that energy would be transferred. Eventually they'll reach a state that's known as thermal equilibrium, where the temperature of both sides, system surroundings, are equal to each other. So how do we measure this transfer? The amount of energy transfer is going to be proportional to the difference in the temperature between the high energy and the low energy objects. So we can say that Q, which is heat, is proportional to delta T, or the difference in the temperature between the two systems or the system and surrounding. Now, how do we make this into an equality instead of proportionality? We're going to need some kind of a constant. So we're going to say that Q must be equal to some type of a constant times the difference in temperature. Now, what is this constant? This same equation, if we rewrite it with respect to the constant, it would say constant is equal to Q over delta T. What that tells us is that the constant is a measure of how well heat is transferred to increase the temperature of that substance by 1 degree Celsius. This constant we call heat capacity, and the symbol of it is just capital letter C. Now, the unit of this very simply is just the unit of heat over the unit of temperature, which is joules per Kelvin, or more commonly you also see joules per degree Celsius. Both of those are the same thing. Degrees Celsius and degrees Kelvin have the same increment. So heat capacity, or C, is an extensive property, meaning that its value will depend on how much material you have. You can see this fairly simply by just thinking about if you want to heat a cup of water, let's say until boiling from its starting temperature of 20 degrees, and then compare to heating a pot full of water, again starting from 20 degrees to boiling. If you use the same method, let's say you put it on a stove top, you notice that it will take you much longer to heat the pot of water because there's just more water in there. And that's what we mean by extensive property, right? The value of C will change depending on the mass of the material you have. Now, you can convert an extensive property into an intensive property by dividing by some measurement of amount. So if we divide by mass, it will just be C over M. We call this specific heat, C sub S. This is something you probably have seen before in prior courses. It's the measurement of specific heat that is independent of mass. Another way to convert this is to use number of moles. So we can take heat capacity and divide it by N, or number of moles, and that's called molar heat capacity with the symbol C sub M. There's some values here of specific heat, and as you can see, some substances have very low specific heat, like gold, for example, and some substances have very high specific heat, namely water. So the way you interpret these numbers is that to heat gold to increase its temperature by 1 degree Celsius requires only 0.1 joules for 1 gram of gold, whereas for water it will take 4.1 or 4.2 joules for 1 gram of water. So if you divide those two numbers, you can see that it takes almost 35 times the amount of energy to heat 1 gram of water to that same increase in temperature. So water is a lot more resistant to changes in temperature. So this is one of the important things about living on Earth, is because Earth has a lot of oceans. There's a lot of buffering mechanism so that the temperature doesn't go up or down very drastically from morning to night, right? You can sort of compare this to areas on Earth where there's desert, where you have mostly sand. You can see that in those areas, the morning temperature and the afternoon temperature and the night temperature can differ significantly. How do we determine specific heat? You take a sample of substance you want to determine specific heat of, like some kind of a metal like lead, for example, and then you would just take that sample, you measure the mass, and then you would heat it up from one temperature to another temperature, and you're going to measure how much energy is being used to make that heating occur. And then once you have that, then you just need to divide the heat by the temperature change that occurs, let's say from 22 to 28.8, and then the mass of the lead itself, and that will give you the specific heat for that metal that you're measuring. So given that we have these three different heat capacity related quantities, we can calculate heat, or Q, three different ways. If we know the heat capacity and we know the change in temperature, we can just multiply those two numbers. That will give us the heat that is transferred, the C, times the delta T, the difference between the two temperature. If we have specific heat, we can just use mass of the substances times the specific heat times delta T. If we have molar heat capacity, we would use number of moles, N, times molar heat capacity times delta T. Now I want to also talk about how we apply this to chemical reactions. So one of the most confusing things I think for students is that there's two different types of systems and how they transfer heat. And the calculation of each of these systems will depend on what it is that we have in front of us. So the first one is the simpler system. In this one, you don't have a change in potential energy. Okay, so potential energy has to do with chemical bonds, right? Interactions between particles and so on. So in this type of systems, there is no change in the potential energy. All there is a change in thermal or kinetic energy. Okay, so you have a system and you have a surrounding, and in one case the system has a higher temperature and the surrounding has a lower temperature, or vice versa. So it's very similar to this picture that I just showed you earlier. So we don't care necessarily about the interaction between one red particle with the other red particle. We consider that not to change between going from here to here. And same thing with the blue, one blue and the other blue when going to the purple. So in other words, the potential energy, which is the interaction between the particles, remain the same. However, the temperature changes from going from this beginning state to the final state. So for those type of calculations, all you need to do is to make sure that the heat that's released by the system that's at a higher temperature, the hotter system, should equal to the heat that's absorbed by the lower temperature system. So an example of this type of system would be if you mix a hot metal with cold water, for example. You can imagine what's going to happen is the metal is going to cool off and then the water is going to heat up. If you mix two types of water at two different temperatures, hot and cold water, which is something that we do almost every day, right, when we're washing our hands, that can be calculated as well using this method. So let's take a look at this example on calculating thermal equilibrium situations where you have two systems, or a system and surrounding, where there is no potential energy change. So this question came straight from your notes. It says you heat 22.05 grams of a solid in a test tube to 100 degrees Celsius and then add the solid to 50 grams of water in a coffee cup calorimeter. It's not important what that is right now. You can just imagine that to be a container. We'll talk more about that later. The water temperature changes from 25.1 to 28.49 degrees Celsius. Find the specific heat capacity of the solid. It's useful to draw this out. So we're starting here on the left with the picture of the solid in a test tube that's being heated to 100 degrees Celsius. Once it reaches the 100 degrees Celsius, we're going to put that hot solid into a container of water, which is marked number 2 here. The water is at 25.10 degrees Celsius. The hot solid, which is now shown in red, is going to release some heat because it's hotter than the water. And of course, the solid is going to cool off. The water is going to heat up. And so eventually they're going to reach thermal equilibrium. Both objects, water and solid, are going to have a temperature of 28.49 degrees Celsius. What you need to do here is to understand that you have two systems, right? Solid and water. One of those systems is releasing heat and the other one is absorbing the heat. So there's conservation of energy here, conservation of heat in this case. Which one is releasing heat? Well, based on the picture that we drew there, the solid is the one that's going to release heat. So because it's releasing heat, I'm putting a negative in front of the Q of solid. That tells me that that system is releasing heat. And then I'm going to put a positive next to the water to indicate to me that that side is absorbing heat. So negative Q of solid is equal to positive Q of water. And then what we do after that is we choose one of those three different methods to calculate Q, either heat capacity times delta T, specific heat capacity times mass times delta T, the MCAT equation, or molar heat capacity times number of moles times delta T. In this case, since the information we're given contains mass and we know it's water, so we can find out the specific heat of water, we can just go ahead and use the MC delta T or MCAT formula. So you see on the left side here, what I've done is open up that equation so that instead of just Q, I am writing mass, C sub S, and delta T for the solid. I keep the negative sign there at the beginning. Now on the right side, I have water for the three components as well: mass, specific heat, and delta T. My goal here is to solve for specific specific heat of solid, so I'm going to do a little algebra to move everybody else on the other side of the equation. Then I should get this expression right here where I have the mass of water, C sub S of water, and the delta T, which is just final minus initial temperature of water, divided by negative M of solid times the final minus initial temperature of the solid. Now everything is in parentheses because I want to make sure the negative sign is outside of the parentheses. Now I put in the numbers. You can look this up for the specific heat of water, and then for the temperature, very important. For water, final temperature is 28.49, initial temperature is 25.1. At the bottom, the final temperature is the same because the two systems are at thermal equilibrium with each other. The beginning temperature of the metal is 100 degrees though, so you got to make sure that you put that in. And as you can see, this will give you a negative value, but the negative value will cancel out with that negative sign that you put outside there, and that's the reason why you need to include that in your original calculation. So the negative has to be there, otherwise you're going to get the wrong answer. Once you do the calculation, you should get this as your answer, and that would be the specific heat of the metal. Now the second situation, which is the one that's more interesting to us, is when a potential energy change occurs in the system. So when would that happen? Well, that happens anytime there's a chemical reaction, because a chemical reaction is really just a breaking and forming of chemical bonds. So if you have a chemical reaction, that means that those bonds, which correspond to the potential energy of the molecules, of the particles, are changed when it goes from the reactant form to the product form. Now the question is, how do we measure the heat that's transferred when that type of situation occurs? In situations like this, when you have a chemical reaction occurring in either aqueous or gaseous conditions, the system and the surrounding are sort of mixed together. They're really hard to tell apart. If you have a container that looks like this, you have your system, which is your reactants and your products, right? And your surrounding is just the water around it, right? So as that reaction is progressing, the reaction might release heat to the surrounding. The reaction might also absorb heat from the surrounding. And we're going to talk about those two terms later on, exothermic, endothermic. But right now, just understand that the system itself or the reaction itself is completely mixed in with the surrounding. In your head, you have to imagine that there is a barrier between them, but in reality, of course, they're all just mixed together. Now, how exactly does the process occur that allows us to measure this heat transfer? In other words, if I were to break a bond between carbon and oxygen, for example, and form an oxygen-oxygen bond, there's going to be a potential energy change, but how do I measure that potential energy change? Because potential energy doesn't impact temperature, right? So how do I actually measure it? So this is how we're going to think about it. And here I'm just illustrating this with a reaction where heat is being released, okay? So first you start, so here's your original reaction. When you have your reactant and you have your surrounding is given here in the blue color. You have your system, which is your reactants. And we're going to say here there's some temperature T1 at the beginning. So the system and the surrounding are both at temperature T1. The two reactants look like this. This is reactant 1. It has that kind of a bond. This is reactant 2. Then the reaction happens. The reaction involves the breaking of some bonds and the forming of some other bonds. So now what ends up happening is you have these products now. So this bond is broken, and then the black atom combines with the blue atom to form these new species here. In this specific reaction, heat is released because those bonds in the product are more stable than the bonds in the reactant. And this is analogous to if you take a ball and you drop it from 3 feet above ground to ground. When that happens, energy is released, right? We can hear it because the ball will release a sound, which is the sign that energy has been released to the air surrounding the ball. Same thing here. The bonds here are more stable than the bonds here, so energy is released. Now, how is that energy released? The energy is released in the form of thermal energy, which is heat. That at the beginning, the system and surrounding are both at temperature 1. Now, the system is at temperature 2, which is higher than temperature 1. Why? Because the bonds are different now, and that excess energy is now released to heat up the system. The surrounding, though, is still at T1 because the system and the surroundings are all mixed together. So what the system is going to do is transfer that energy to the surrounding. So that heat is then going to flow to the surroundings, bringing the temperature of the system back down to T1 because now the heat is gone, so it's back to wherever it was before. And the surrounding now, because it's getting that extra heat, is now going to be at T2. So what we notice in terms of the reaction, if we're the one carrying out the reaction, what we notice in the container is that we see initially we have reactants with the surrounding at T1. Let's say that's my water. And then now I have my test tube again, or my container, but now the temperature of that water is higher. Now it's at T2. My system is the same, but now in this case I have product. Okay. Okay, I observe the difference in temperature between the surroundings at the beginning and at the end, and that difference in temperature I can multiply with a heat capacity in order to get the energy that's being transferred when that reaction occurs, when that reactants get converted to product. That's really the idea of how we're going to measure these energy transfer. That heat that I drew here is called heat of reactions. Now, reactions don't always generate heat. Sometimes reactions absorb heat. So in other words, this bond is more stable than that bond. So when you make the product, you actually need heat to come in from the surroundings. So in that case, the picture is flipped. You start with the red picture, which is the higher temperature, and then you go to the lower temperature. And so those two types of reactions are given different names. So if the system releases energy, which means it increases the surroundings temperature, we call that exothermic. X is to push out, therm is heat. So heat is released. Now remember that for exothermic reaction, the sign of your Q is negative with respect to the system, right? Because heat is released from the system. Now, on the other hand, if your bonds of the reactant are more stable than product, then energy has to be absorbed, right, in order to make your product. So in other words, you can draw this again, but then heat now is flowing in from the surrounding into the system to make this happen, to convert that to the bond. So because there's absorption, the surroundings temperature decreases, so it gets colder. Again, you're in the surrounding, you're not in the system, you're not the reactant, you're not the product, you're a surrounding. So if you hold that test tube, you're going to feel that it gets colder. Those reactions we call endothermic, and the sign of Q with respect to those reactions is going to be positive. So let's take a look at a situation where the potential energy is changing, so there's a chemical reaction, and how that potential energy change is then being transferred into the thermal energy change of the surrounding. So here it says you have two aqueous reactants at 20 degrees Celsius. You put it in a container. Again, it's called calorimeter, which we'll talk about in the next section. The reaction happens, and then you have a thermometer in there to see what the temperature is at the beginning and after the reaction is complete. The question is, what's the heat of the reaction? Remember that the heat of the reaction is a component from the reaction itself, right? If you recall the drawing we had in the lecture notes before, that there is a certain amount of heat that's either released or absorbed by the reaction that accompanies the change in the structure of the molecules from reactants to product. Okay, so the heat of the reaction measures that change, the relative stability of the bonds in the product versus the reactant. We have the reaction at the beginning where we just have reactants and we're at 20 Celsius. We have some kind of a container with thermometer in it, so the thermometer currently has 20 degrees Celsius on the mark. You let the reaction occur, and afterwards, once you have only products in it, now the temperature has dropped to 18.5 degrees Celsius. So the question then is, what's the heat of the reaction? What kind of reaction do you have, exo or endothermic? You start with Q system is equal to negative Q surrounding, or you can also say negative Q system is equal to Q surrounding. All we're saying here in that equation is just that whatever happens in the system, the opposite is happening in the surrounding. This is with respect to heat transfer. So if the surrounding is absorbing heat, then the system will be releasing heat. If the surrounding is releasing heat, then the system would be absorbing. So that's all that equation is saying. Our system in a chemical equation is always the reaction. So in other words, reaction and system are interchangeable. Okay, it means the same thing. What about the surrounding? Well, this goes back to that idea that I mentioned earlier, that the surrounding is often mixed up together in the system. You just have to keep in your mind that you have water and then you have reaction. It's really hard to separate them out, right? In fact, they're not separated physically, but in your head, in terms of calculating energy, you have to separate them out. So what comprises the surrounding? Well, it's going to be the solution. Basically, everything else that's in there. That's not a reactant or a product. So how are we going to do the calculation? Well, look at the numbers that were given. We were told the mass of the solution, the specific heat of the solution, and the final temperature of the solution. That means that would allow us to calculate the Q of the solution. And that's what I did here. I just multiply mass times specific heat times delta T. Mass is 5.8, specific heat 4.1. Now here's the delta T. The final temperature is 18.5. The beginning temperature at the start is 20. You notice that when the answer has a negative in front of it because your delta T is a negative number. So negative 35.67. That is the Q of the solution. Remember, that's the Q of the reaction, or if the system is going to be negative, the Q of the solution. So if the Q of the solution is negative 35.67, 35.67, then the negative of that number is positive 35.67 joules. So that would be the Q of your reaction. Seeing that that's a positive number, that tells you that the reaction absorbs heat and that reaction is an endothermic reaction.